Today I'm going to be talking about secure boot and specifically like how it works on Linux, because I haven't used Windows recently. So yeah. So secure boot is for a lot of people. It might be for you if you have a roommate or if you have other people who are not family in your house. Also, if you have a laptop, you might want to be, and you're using Linux, you might want to be using secure boot. Now, some Linux distributions come with secure boot. That's great. I'll explain why that's bad later. If your distribution requires you to disable secure boot, I'll show you how to enable it. Secure boot might not be for you if you use a really old computer. Note that this ThinkPad is actually running core boot. If your computer is old enough to be supported by core boot, then you actually can have secure boot, because you can use the EDK2 payload, if you know what that is. If your computer never leaves your home and no one else is allowed in your home, there's really not any point in doing it. You should still use full disk encryption though. If your BIOS is full of bugs, do your research before attempting to use secure boot, because if you don't, then you might accidentally break your computer. Sometimes doing something weird to the boot configuration can break it. Sometimes doing something normal to the boot configuration can break it, so do your research. All I can tell you is that that computer is a Dell Inspiron 7405 2-in-1, and it works, mostly. Also, NVIDIA GPUs have their firmware as UEFI option ROMs. And what that means in practice is that it also gets verified as secure boot, and they're signed by Microsoft's keys. So you either have to add Microsoft's keys to your computer or sign it yourself every time, and neither are very much fun. So like with a lot of other things on Linux, if you have NVIDIA, you're gonna have a bad time. So first, I'll explain how secure boot works. First, the platform verifies the UEFI, at least in theory. The firmware doesn't actually have to be verified according to the UEFI specification. In the specification, it only defines the interface with the firmware and implicitly trusts the firmware. This is fine if your firmware is immutable and bug-free, but it's not, especially on Dell. So the UEFI platform root of trust is the firmware. And in order to ensure that the firmware is actually trustworthy, the physical platform root of trust will probably be something other than the firmware that verifies it before starting it. On Intel, this is the Combined Security and Management Engine. Also, yes. Oh, it's the thing that does secure boot. The modern version of BIOS. But really, it's just the thing that does secure boot for the purposes of this talk. So the platform root of trust can be the Intel Combined Security and Management Engine on Intel processors. On AMD processors, it's the AMD Platform Security Processor. People tend to hate on these things because they have proprietary stary firmware. The Intel one is especially stary, and the AMD one we don't know very much about, which either means it's more stary or less stary, depending on how you think of these things. On some Dell computers, especially enterprise stuff, the root of trust is the embedded controller, which is normally the thing that like handles your fans. And that's the root of trust. And then on HP computers equipped with HP SureBoot, the root of trust is the HP Endpoint Security Controller, which is their own chip that they decided to put on the motherboard so they could write white papers about it. This is all just fancy words for, in general, you have hardware that verifies the UEFI firmware is signed using a key that's stored in read-only memory. All it does is verify it. That we don't really care about anything else that it does, unless you're a conspiracy theorist. Yeah, here's the first how to do it wrong slide. There are several more. In 2020, last year, some laptop manufacturers are found out to be disabling boot guard when resuming from S3. Boot guard is the thing that's part of the Intel Combined Security and Management Engine that verifies the firmware. So what you could do is put a computer to sleep, that's S3, and then flash the firmware, and then turn it on again, and it wouldn't check. Why would you do this? Yes.
Does this just last until the next power cycle, or does it last forever?
The flash lasts forever, but the next power cycle it will check.
And it'll like fail to check.
Yeah. So it'll break.
Yeah, I guess it was the difference between sleep and like shutting down.
So when when you suspend your computer, you can turn it on again really fast.
Yeah.
It's that thing. Okay, so the reason that this vulnerability exists is the code path diverges where it would normally initialize the memory controller, because the memory is already on when you resume from suspend. So they had a setting where you could go to the boot guard part from there if you wanted to, and the manufacturers are just turning it off. And it turns out that Microsoft had a requirement that laptops had to be able to resume from suspend in a certain amount of time. And for manufacturers with slow processors or slow motherboards or something, they made up that difference by completely ruining the security of the secure boot. So they all changed that after the fact. And the great thing about this is it actually was better to ask forgiveness than to ask permission. Because now that these laptops have already been verified to run Windows by Microsoft, now they can patch the vulnerability and it can be too slow and they can get away with it. So anyway, the UEFI firmware has a bunch of different keys that it uses to verify the payload, that is your operating system that's being booted. The root of trust for these keys is the platform key. And the platform key, there's only one of them, and you can only install it once. After that, you have to reset the secure boot settings in order to install a new one. The platform key signs a key exchange key, and the key exchange key, there can actually be more than one key exchange key, but they all have to be signed by the platform key. They all have to be installed at the same time as the platform key. So they're, for our purposes, immutable. And I swear there's a reason for all this. The key exchange key signs updates to the DB and the DBX. DB stands for database and DBX is database something, I don't remember. And the DB stores signatures, or it stores signing certificates and hashes of binaries that are allowed to be booted on the system. And the DBX stores revoked certificates and hashes that should not be booted. So for example, there was like some antivirus vendor had a bootable disk, and it turned out that you could make it boot anything and it wouldn't verify it. And so Microsoft added the hash for their bootable disk to the DBX because it was breaking the chain of trust. So who owns the platform key? Does anybody know like what entity has control over that? The answer, oh, go ahead.
Is there one platform key per computer or like one in existence?
No. The answer is that your motherboard vendor is the owner of the platform key, and the motherboard vendor signs the key exchange keys. If you have a laptop, the motherboard vendor is the manufacturer of your laptop, most likely, or it's that one company that makes all the ones that get rebranded. Who owns the key exchange key? This one is a trick question. You can answer on Zoom too, because I can hear you. So the owner of the key exchange key, well, one of them is your motherboard manufacturer, because they need to be able to install updates to the BIOS. Excuse me, UEFI, not BIOS. And they also need, they might, sometimes they distribute option ROMs. I don't really understand how that works. But the big one is Microsoft. Microsoft distributes updates to the DB and the DBX for Windows and things that shouldn't be allowed to boot. They also have a second DB key that they use to sign third-party software that they want to allow to boot. So the verification process, let's say you have some Linux. First, it'll be checked against the DBX. I think this is an interesting design choice that they actually chose to check against the DBX first. It'll check if it's hash or if the certificate it was signed with is in the DBX, and if so, it'll be rejected. If not, it'll move on to the DB, and it'll check if it is in the DB, and if it is, then it'll boot. Yeah, Microsoft stuff. So laptop shipped with Microsoft T Exchange key. The DB and the DBX updates are distributed through Windows Update. They're signed with Microsoft T Exchange key. Other operating systems can get bootloaders signed by Microsoft using their DBX key, and it's a pain. I think Ubuntu had some issues with it not too long ago, where their Microsoft wasn't signing their bootloader for some reason. Oh yeah, it's just a bureaucracy. Microsoft is just taking too long. And if it gets approved, Microsoft signs a copy of the bootloader with their DB key, and then they give it to them. With this key signing scheme, that means that every time Microsoft makes a bad signature, they have to revoke not the certificate, but the hash. So the DBX consequently mostly consists of hashes. Yes?
Most OSs just use shim now, no?
That's true. Most Linux distros use shim. I just do that later. And if you do it wrong, then Microsoft has to add everything that's vulnerable to the DB. There was a buffer overflow in GRUB, and they had to do that, and it was kind of a pain. That's generally the theme here. Here's how to really do it wrong. Now, this article is clickbait. They didn't actually leak the secure boot keys. The DB keys, those are safe. What they leaked was a policy that you could apply to devices that were locked to run only Microsoft software. And the policy would let you make secure boot not check. So it would still act like it was in secure boot mode, but it wouldn't check. And it's great for jailbreaking. It's also great for jailbreaking other people's devices without their consent, which is bad. And it's kind of hard to tell too. Hopefully it changed TPM values. I don't know if it actually did or not. It was not. They were thinking about like trying to physically change all of these devices. It was really bad. So also in UEFI, there are two different modes. If there's no platform key present, then it'll be in setup mode, and it'll let you install platform keys or a platform key and key exchange keys. As soon as there is a platform key, it switches to user mode, and you can't change the platform key or the key exchange keys, but you can still update the DB and DBX if you sign them with one of the key exchange keys that is enrolled. When I was setting up secure boot on my laptop, I'd never done it before, so I was doing it wrong in a couple of different ways. And I tried to install the platform key first, and then the key exchange key. But what happened was, as soon as I installed the platform key, it switched to user mode, and then it wouldn't let me install any key exchange keys. And I spent hours trying to figure this out before eventually I just did it in a different order, and it worked. So you have to, if you're booted, like if you're installing the keys from Linux, you should be able to install the key exchange key and the platform key in either order. But I was doing it from the BIOS interface. And so it was switching modes as soon as I enrolled the key. So here's how secure boot works in Linux. The first option is PreLoader, which is signed with Microsoft keys. And it verifies the bootloader and kernel with hashes that are enrolled in somewhere. I don't know where it puts the hashes, probably NVRAM. And in general, it requires physical access to enroll new hashes. And this is a pain because every time you update your kernel, you have to enroll it in PreLoader. So the next option is shim, which is what the person in Zoom was asking about. Shim is signed with Microsoft keys. It's made for GRUB, and it verifies the bootloader and kernel with hashes or a signature. It requires physical access to enroll new hashes or a signature, but shim might come with an embedded signature. For example, shim on Ubuntu comes with Ubuntu's secure boot signing signature. And on some websites, you'll see the mock, the machine owner key. That's something that you can enroll in shim that says, I get to sign what runs on here. And the point of shim is to, well, it's a shim. It lets you check secure boot signatures using non-Microsoft keys, but it is loaded, but shim itself is signed with Microsoft keys. So this is in situations where you don't want to change the existing secure boot settings on your laptop. For example, it would break it because it's Lenovo. Not all Lenovo's are vulnerable, but that was the thing that I had up earlier. And this is great, but the fun one is enrolling your own keys. This is what I did on my laptop, and this is what I actually recommend on Linux. So with secure boot, the goal is not to make it impossible for anyone to modify your system. The only way to do that is using Verity, and that is the worst. Oh, I should not bump that. So what you want to do is make it as painful as possible for anyone to do anything with your computer without your permission, of course. If it's with your permission, then you need to scale back like the i3 and whatnot. Where was I? Oh, right, you want to make it painful. So I'll get to this more later, but you want to make it so that you can't just have any old guy with a flash drive come and tamper with your operating system. Warning. If you have a card with an option ROM, this is the part where you have to either add Microsoft keys to your DB, thereby defeating the purpose of enrolling your own keys, or manually re-sign the option ROM every time it's updated. Sorry, that's what you get for using NVIDIA. Yes. So the option ROM is it's the extra thingy that's the firmware. I don't really understand how it works because I avoid NVIDIA like the plague. So Microsoft keys don't do much to protect you from physical access. Now, like I said, you can't protect fully from physical access, but you want to at least make it so that you need a disk adapter to do anything with your computer. Because like flash drives are cheap and disk adapters are like $30 or something. And you want to avoid opportunistic access. Also, set a BIOS password. If you set a BIOS password, the UEFI spec actually dictates that the secure boot key should reside in delete-resistant storage. So depending on the platform, resetting the CMOS and the password might not be enough to actually be able to change the secure boot keys. I give it about a 50-50 chance of actually being difficult, though. I think on Dell, resetting the CMOS does not reset the BIOS password, so you better not forget your password. So here's how you generate your own platform key and key exchange key. First, you have to generate a UUID, that's a universally unique identifier that identifies the owner of the key. Then you have to generate a platform key. Then you have to convert it to an EFI signature list. Then you have to sign it with itself. Then you have to create a key exchange key, sign that with the platform key. Also convert it to an EFI signature list. Then you create a DB and sign that with the key exchange key. And then you don't have to create a DBX because like you're not going to sign anything bad, right? If you do sign something bad, then you have to create a DBX to rotate your keys. Then you have to sign the binary. In this case, you want to sign the kernel because the kernel is a valid EFI binary. Yes, I'm going fast on purpose. What's the question?
Question chat, do you need any particular OIDs on the search?
Can I read that? Do you need organization ID? No, you don't. Let's see. I think I just set it to, I don't think I even set it in this one. So you sign the kernel. The kernel is actually a valid EFI executable, meaning it can be booted directly if your firmware is not terrible. So you have to sign the kernel, and you also have to sign the bootloader, which is probably GRUB, might be system deboot. System deboot is better, I'll get to that. Then you have to put your firmware in setup mode. This is really annoying because vendors just seem to call it whatever they want. Some of them say delete the platform key. Some of them say switch to setup mode. Some of them say reset the secure boot keys. Some of them say nothing, and you just have to click it and see if you can delete it. But once you put it in setup mode, then you can enroll your keys using SVT sync, which Linux has the directory for keys in sysfs, and you can copy them to that using this program because I don't remember where it actually is. This is all really painful. Also, the platform automatically switches to user mode once you enroll the platform key. This is all painful. So Morten Linderud, also known as Fox Braun, who is an Arch Linux team member, wrote a tool called SBCTL. And SBCTL does it all for you in like 2 commands. So you should use this instead. It's written in Go, it's pretty easy to compile, and it doesn't have any dependencies. So it's very nice. So there are a few problems. You don't want to store your SBCTL keys on an unencrypted hard drive, because what's the point in that? Then someone who does have a disk adapter, like you don't want to make it easy for, you want to make it impossible for people for flash drives, but you also want to be annoying to the people with disk adapters, right? If someone has a disk adapter, they're just going to read your keys and sign whatever they want with it. That's no good. GRUB is bad. On GRUB, the menu isn't actually protected. So people can just like edit the kernel command line and add options and stuff. One of the options, you can tell it what the init should be, which you should set that to the shell and then do a root shell. You can protect the kernel command line and stuff, but you have to manually edit the grub.cfg file that is automatically generated on most distributions. You have to manually edit it every time you generate it, and it gets auto-generated when you update packages that are part of it. So it's no fun at all to do that. And also, this is probably a me thing, but I try to get my boot time as low as possible, because for a while my computer didn't support sleep. And bootloaders are slow. So general recommendations, you might not want to use GRUB. If for secure boot, system deboot is generally better. You want to validate all boot configuration with secure boot. So you don't want to, so that's the problem with GRUB, is that the grub.cfg file, someone can just edit that if they have a disk adapter. That doesn't protect you from anything. You can set, and like, even if you set the password on GRUB, they can still edit the grub.cfg file. You can't encrypt that file. You need to validate the initial RAM file system for the kernel. You need to validate the kernel itself. That's probably already done. But the initial RAM file system is generally not validated, which is problematic. Don't use Microsoft keys, because if you do use Microsoft keys, then someone with a live USB can just boot that. Like, for example, the Ubuntu USB, that uses shim, so you can boot that on a computer that has secure boot enabled. Set a BIOS password to make it annoying. Use EFI stub when available. So EFI stub is this really cool idea where you merge the init-ramfs, the kernel, and the kernel command line all into this one big blob. And then that is signed. So that you take one signature and it verifies everything that you need for booting, and it won't boot anything else. There's a really great article on how to set it up for Arch Linux. I haven't tried it for other distributions, but it's probably not terrible. Don't quote me on that. Also use disk encryption. Don't just use it in combination with secure boot, use it in general. I recommend requiring a password at boot and then using sleep mode so you don't have to hit the hard drive every time you turn on your computer. Make sure you're actually using deep sleep. If you think sleep drains your battery, it's probably because you're not. Microsoft introduced this new thing called modern standby, where the computer will just sort of, it'll keep the CPU and Wi-Fi and a couple other things active so that you can get notifications and stuff. And it drains battery like you're just using it normally. And it's really unpleasant. On Linux, sometimes it'll select suspend to idle. That's what Linux calls it by default. You want to make sure deep sleep is selected by default, and you can tell which one is selected by doing that command. If you have S2 idle selected, it's pretty simple to switch it. Just add mem sleep default equals deep to your kernel command line. You might have to enable a BIOS setting to actually be able to choose deep sleep. for a while, there was a Windows bug where if a computer supported both S2 idle and deep sleep, Windows wouldn't work. So what manufacturers did was they disabled deep sleep on their computers, which is terrible. Lenovo in particular has a switch in the BIOS that you might need to switch to turn this on. On any Dell computer made after like December 2019, just supports S2 idle, which is awful. On Dell computers, you might be able to hack the ACPI table to enable sleep. Because what the deal with my laptop is they have a switch in the BIOS, just like Lenovo does, but it's hidden, and so you can't actually use it. So, what you can do is you can get into the ACPI table and make it so that it just ignores the switch and always enables deep sleep, which is really great. So I've done that. Yes. It's kind of out of the scope of this talk. I was just mentioning this, but I might go into it in more detail another time. Basically, it's the way the UEFI firmware gives data to the operating system about how to interact with it. And so you can abuse it to make the operating system tell the firmware to do things that the firmware didn't want you to know that it could do. You can also approximate sleep with hibernation and full disk encryption and the trusted platform module. The TPM, you can use it to only unlock encryption keys if the system state matches some certain predetermined state. For example, what I was using for a while on my computer before I figured out that you could hack the ACPI tables was I would make sure that all the secure boot settings were the same. And if they were, then I knew that only the operating system that I wanted would be able to boot. And so then I would automatically unlock the encryption key. That way I could resume from hibernate fast. Do not hibernate to an unencrypted slot partition, because then people can basically edit your RAM. And that's no good at all. I don't recommend doing this. It has a really huge attack surface. And there's no way to pin the encryption key. So someone could, in theory, set up an entirely different encryption key and just overwrite part of your hard drive with that, and then boot to that and unlock the actual key using the TPM, and then unlock your disk image offline. That would suck. Also, just in case you're curious, Chrome OS uses something completely different than UEFI Secure Boot. Chrome OS uses Core Boot, and the payload is Depth Charge, which is developed in-house at Google. And Depth Charge is just like a pretty custom verified boot implementation. It's open source if you want to go look at the source. It's kind of interesting, but there's not a lot of documentation. Android is, I don't really want to talk about Android, but the reason I put this on here is that there are a couple of Android devices that actually let you change this, or at least add a secure boot key. So for example, on my phone, I'm running Graphene OS, and Graphene OS is signed for verified boot, and you can actually relock the bootloader after installing a custom ROM. As far as I know, only Google Pixel and OnePlus devices will actually let you do this. So there's not really a lot you can do there. All right, what time is it? Awesome, I have a demo. This is what you can do with physical access to a machine. Also, if you have any questions, now's a great time to ask them. Yeah, go ahead.
So I think on the slides have like PM and FDE, right?
FDE, full disk encryption.
Okay, so FDE is what is TPM?
That's the trusted platform module. That's the thing that you can use to make sure you boot it securely. Yes, Zoom chat.
What is the threat model for this level of setup?
So it's sort of wishy-washy, but in general, the threat model is you don't want someone like with a Ubuntu Live USB to be able to boot that on your computer and start reading stuff off of it or tampering with your operating system. And you also want to make it painful for someone who wants to try that with an actual hard disk adapter. So basically, another CS student. So here's, let's see. I have an Ubuntu virtual machine over here. Oh, gotta enter my password. I have an Ubuntu virtual machine, and oh, I forgot to hang on a second. I did a stupid thing. Okay, there we go. Yeah, this is the one I want to run. I have this Ubuntu virtual machine, and here's what happens if you just use Ubuntu's default GRUB config. Oops, I hit escape too many times. Now I have to start over. All right, so take two. You can just hit E to edit the command line, then go down here and say, oh, I forgot, this is actually not going to work on this demo. Maybe I have a different one that I can try. Let's try Fedora, maybe that'll work. Yeah, okay. So what you can do is just go on here, go to the end of the command line, and add init is bin bash. And then hit Control X to start. And you get a root shell. Nice. So this is with no secure boot and no full disk encryption. Normally with full disk encryption, you could get a root shell with the hard drive unencrypted, because obviously you don't know the password. But for some reason on Ubuntu, it doesn't work because they had a really custom setup. But now I will demo what you can do to Ubuntu. So this is an Ubuntu virtual. I want to exit. This is fun. Watch this. If you exit from bash when you do this, you get a kernel panic. It's not actually showing up. It probably crashed the graphics driver too.
Is that because init is never supposed to stop?
Correct. The question was, is that because init is never supposed to stop? And yeah, that's if that happens, it says you tried to kill init and it kernel panics. So here what I have is an Ubuntu virtual machine using Microsoft's keys for secure boot and full disk encryption. This is to showcase what's wrong with the GRUB. So you have to enter a password to log in. The password is password. Or sorry, not to log in, to boot. And then once it boots, I'll log in and show you what the system is set up to do. Oh, I want to make the screen bigger. Yeah, there we go. So I'm going to open disks and show the disk layout because I don't know, it's kind of interesting. So what we have is we've got the UEFI system partition. That's the partition that contains the bootloader. Then we have boot, which contains the boot files. Then we have a single LVM partition with the encrypted partition taking up the full space, which is really confusing. The only way to enable encryption on Ubuntu is to select LVM and encryption. And like, it just creates this empty LVM, or not empty, but full LVM volume. And like, what's the point? If you don't know what this means, LVM is something that lets you, it basically lets you have more than one partition on a single disk partition, and it's really easy to move them around and stuff. And normally you would want to have more than one partition on LVM because like that's what it's for. But Ubuntu just did it like this. I use the automated installer. Anyway, this is the encrypted partition. it's unified key setup. Now, what I'm going to do is I'm going to plug in an Ubuntu Live CD, and I'm going to tamper with the system. So first I'll shut down. And now I've got an Ubuntu Live CD here. And I'll apply that. And I'm going to copy a link to my clipboard. Let's see, where did I put this? Yeah, here. I did that off screen on purpose, just for not because it's secret, just because it would be kind of messy. And now I'm going to boot to this dist. And this is the Ubuntu Live CD. Ubuntu Live CD takes longer to boot than regular Ubuntu. What the heck? Okay, seems fine. Not sure why it turned upside down there. It's running on a virtual machine, so maybe it did something silly. There we go. So what I'm going to do is I'm going to open up Firefox, and I'm going to go to this link that I prepared beforehand. I am going to manually input the link from my keyboard because I cannot copy and paste. So first I got to change my keyboard layout because I used Dvorak. I do. It's because I had a bunch of bad QWERTY habits because I didn't properly learn how to do QWERTY. So instead of like properly unlearning the habits, I just picked a different keyboard layout. Oh, this part takes forever. I have to put. Oh, never mind. That was quite fast. That was nice. Oh no, it didn't actually click. There we go. Okay, I got Dvorak. Now delete the English. Okay. So what this is a malicious version of the initial RAM disk that I made. And it's going to do something slightly different. Okay, so the initial RAM disk, in case you don't know, is the thing that gets loaded in by the kernel when you're, that's what takes in. It gets loaded in by the kernel into RAM, and it's the initial file system. And that file system contains the init that file system is responsible for getting the system to a state where it can actually read your hard drive. So all the encryption stuff, that's going to be handled in the init ramfs. So we're going to take this file and we're going to open up a terminal. Actually, I'll use the disk just because it's nice, pretty gooey. I'm going to mount the boot partition, and I'm going to copy it, or I'm going to take the initial RAM disk, the malicious one, and copy it over the one in the boot partition. And that's the 5.034 one. And remember, this is running the live system, so I just tampered with the boot files for the system that's installed from the live disk. I'm going to unmount that. Don't need that anymore. Don't need that anymore. And I'm going to reboot. Oh yeah, wants me to unplug the virtual disk. Sure, I'll do that.
It doesn't actually check whether you do it. Just wants to press enter.
I know, but I also meant to remove it at this point. So I did. So now it looks the same. Password is password. There's no obvious difference in what it's booting. And we can look at the disk layout. Nope, not that. Disk layout is the same. Nothing's changed in my files or anything. But now we're gonna say, okay, I've done some work on the computer. I've shut down, and the person who had the flash drive came back. And now so we're gonna boot from the live disk again. Oops. It's just as painful to get into the boot menu on the virtual machine as it is on a real machine. Except I already know that the escape is the button I'm supposed to press. Yeah. So now we're going to boot the live disk. Oh, did you have a question?
The question in chat, can't you achieve the same thing with a keylogger?
Well, suppose it's a laptop and the keyboard is built in.
I don't know what this is.
Well, because you're the one who asked the question. Yeah, so remember this happens in the init-ramfs, and so you can't actually like install malware on the host system and expect it to transfer properly to the init-ramfs.
To clarify, I mean, this is not an opportunistic attack.
It depends on what you mean by opportunistic. It's
Requires repeat exposure to a malicious.
Oh, I see what you mean. Well, see, the thing is, what I made was a keylogger, and I'm about to show you what it did. At first I thought you meant hardware keylogger. So we're going to mount the UEFI system partition. And there's a new file on here called P. And this is what I typed in at the decrypt the drive prompt.
So now you know the password for the full disk.
Right. And in theory, you could do way more. You could put malware on the init-ramfs that loads after you enter your password and sends the keylogger over the internet. That's hard, and I only had an hour to do this, which is why it's only writing it to a file in the UEFI system partition. But in theory, you could log the password and then pass that data to the host system and send it over the internet. Or you could just put malware on the host system. Yes.
If you like run code off the ramfs, does that stick around once you move into the PLOS?
It's complicated and it's different per distribution. But on Arch Linux, which is the one I'm more familiar with, the file system doesn't stick around because it switches root, and it switches to a different init. So you can't really expect processes to stick around. But there are ways to do state transfer with systemd. Let's see. Does that make sense? Yeah. You can do state transfer with system D. You could temporarily put it on the UEFI system partition and then read it out from the host system. And you can, what you can do is do anything to the file system of the host system from the init ramfs, because the init ramfs is the one that's responsible for opening that in the first place. And yeah, as a reminder, this happened because Ubuntu doesn't check the init ramfs with secure boot. If you use EFI stub, which I mentioned earlier, you can combine the init ramfs with your kernel and sign that, and it wouldn't be vulnerable to this attack. And that's what I have. I'm
We
good.
have baked goods up here if y'all want to form an orderly line and we can distribute them. Yeah. No problem.
I'm glad my computer didn't kernel panic. Not that that's happened before or anything.